And you still won't know why. Greetings and welcome, friends of all ages, mathematicians, and I guess even biologists. We're taking a look at page 565. We were talking about graphing polar equations, which are quite interesting. I mean, prior to this, we did like graphing a circle at the center of the pole or a line passing through the pole. But now we're getting into some interesting stuff here. So here's question 13. And it says r is equal to 3 times theta. So as my angle changes, as the theta increases, the value of the radius is increasing forever. So what this ends up being is a spiral of Archimedes is what's going on here, which this sort of equation can be used to model a magic conch shell falling right out of the sky. So spiral of Archimedes. And the thing that I'd want to point out is that theta only works in radians because 3 times 60 degrees would be 180 for a radius, whereas 3 times 60 degrees in radians would be pi over 3, and 3 times pi over 3 is just pi. So 3.14, the value of pi, is way different than 180 for a radius. So there has to be some sort of consistency, should I say, with the use of radians for your values of thetas. So there we go. So one of the things you could do is make a table of values, all sorts of different things. I'm just going to kind of go through the angles. And so let's see. When theta is equal to 0, I'm facing this direction. And where am I moving? 3 times 0 is 0, so the radius is 0. Right? Okay. When theta is, let's do the pi over 3 like I said. So here's pi over 3 or 60 degrees that I'm facing. And 3 times pi over 3 is pi. So that's like 3.14. So when I'm facing this direction, I'm going to go out 1, 2, 3, and a little bit more. So it's somewhere like right around here, I'm guessing. All right. I like that. How about what is, well, actually, let's throw a pi over 6 in there. That's the 30 degrees one there. Pi over 6 multiplied by 3 is pi over 2. Half of pi is like 1.6-ish, right? 1.5-ish. So in this direction, it would be like here-ish. Here's 1 and a little bit more. I don't know, something like that. So far, I've got the spiral going like that. Let's see. Pi over 2 is 90 degrees multiplied by 3, so that's 1.5 times pi. So I'm thinking like 1.5 times, if pi was 3, rounding, clearly. I mean, I could get this from a table in my calculator, which I have as well. But I won't do that, please. 1.5 times 3 would be like 4.5. Am I right? So at this, I'd be up at 4.5, something like that. So it's actually getting further and further out as time goes on. Let's see. So I did pi over 3. 2 pi over 3. Is that this one here? I think so, yeah. 2 pi over 3 multiplied by 3, the 3's cancel out. That's 2 pi, so that's 6.28 is how far I would go out in this direction. Here's 6 and a little bit more. So this spiral is like getting further and further out. Let's see, what's another good one I could do that cancels with a 3? What's this angle? This is 5 pi over 6, I believe. So that's going to be the same as 5 pi over 2, 5 halves 2, 2.5 times 3 is going to be, what, 7.5-ish, a little more. So in this direction, here is, let's see, did I put that 6 in the right spot? 5, 6, no I didn't. Here's 6, my bad. So 7.5 is, or 7 and a little more is over there. So I just want to point out the radius is getting further and further from the pole as we loop-de-loop and pull. So, some other values that I could work with here. Whoa, slamming my calculator. Let's see, when I've got, let's see, actually I think the thetas.
So if you want to do like the table and you want to change degrees to radians, you do pi over 180 or, and that'll change.
Oh wait, no, that's radians. It's 180 over pi.
Here, let me see if this will work. So here, what I've got going on is I actually went to mode, And there's actually a way to enter into polar mode on some calculators, which is cool. And I also was in Radian mode. And so I hit y equals, and I've got 3 theta. And I'm actually just looking at a table here. I was coming up with all my values on my own here. But here's my table. So this is in radians. So pi radians would be a little bit more than 3. So it's saying 3 radians would be around 9 for the radius, or exactly 9. So a little bit less than this, it would be at exactly 9. 4 radians would have been somewhere around here. And the table's saying that 4 times 12 is 3, right? So 4 times 3 is 12. My B, friend. My B. So that's somewhere around here. 5 radians, I think. Actually, or is that? No. Let's see. 4 radians. What is 4 divided by pi? 1.2. So yeah, 27. Yeah, somewhere around there. Somewhere around here. And then let's see. What did I just say? 5 radians. I'm trying to figure out. 6 radians is somewhere around here. 5 radians must be somewhere around here. I can't decide which side of that it's on, but it doesn't really matter. 5 times 3 is 15. And so let's just say it's like right there. So you can see that this is a spiral of Archimedes. And it would just keep getting further and further out. And it actually keeps looping forever if you have an unrestricted domain for theta. So that's kind of what we've got going on there. Actually, let's just, for funsies, check the calculator. So I've got r equals 3 theta. Let me hit graph to see what happens. Whoa! There it goes. That was fun. Thanks for watching that. Let's see. Let's take a look at one more problem. I've got r equals 2 times sine of 3 theta. Oh, this one's going to be interessante. So 15 here. I was thinking of doing this rectangularly, but that 3 is actually going to mess with the period of the sine function. Well, let's think about it, though, nonetheless. Let me flip on over to a rectangular coordinate system. Actually better than that. I want to switch over to trigonometric axes. Yeah, that's good. So let's see. I'm trying to think if it's cycling back through that 3 times as quick. Yeah, this'll do. This'll do. I'm working on it here. I've got a nice little grid form in here. Oh, there we go. So if I wanted to graph y equals 2 sine 3x, let's say. All right, now multiplying the x times 3, you might remember that's actually going to shorten the period into thirds. All right, so the regular period would have been 2 pi. So cutting 2 pi into thirds, 2 pi over 3 and 4 pi over 3. So I'm actually going to get like a full sine wave in each of these or whatever. All right, so within 2 pi radians, 1 full revolution of all my angles, I'm actually going to cycle through these lots of times. You might remember when we were graphing on the geometer sketchpad yesterday, when I had the n value change, that whenever n was odd, that was the same as the number of petals. Whenever n was even, there were twice as many petals going on. So I'm expecting 3 petals, and that's what we should end up with. Now the 2 here is just going to change the amplitude of my sine wave. So it's going to go from like this to the full 2 to 0 to the negative 2 to this, and then like repeats. So it's actually like, so the radius is going to be all over the place. So remember that this is going to represent our radius. Whoa. This is exciting, guys. Ready? Here we go. Click, 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 click. Whoa! Man, I felt those G's. So, all right, here we go. So let's represent this graphically. So I'm actually expecting, how far out on my polar axis should I go for my maximum radius? 2. Exactly. Because I see that the y values here are only ever going to be between 2 and -2. So for my polar axis, I'm going to experience the same sort of thing for my r. So my making that little graph is the same as essentially me having made a table of values. I'm just kind of using it as a reference. Okay, question?
Yes, so if the 2 was a 5 instead of like any number.
Then this would have been going as high as 5 and -5.
Okay.
Yep.
So, alright.
Yep, good question. And actually think about the fact that the values of sine of any angle are only ever going to be between 1 and -1.
Oh,
So multiplying 1 or -1 is just, it's scaling it, right? So that maximum is going to be 2 times 1 and the minimum is going to be 2 times -1. And that's why you can see that it's fluctuating between those values. So let's see, from 0 to pi over 3. So from 0 to pi over 3, I'm fluctuating from from 0, right? At halfway between that, it's going to actually be at its maximum value of 2. And then back at pi over 3 when I'm looking this way, it's going to be back at 0, right? Because you can see that it went from 0 to 2 to 0, all within that. And halfway between that at pi over 6 is when it would have been at its maximum. So that's what I'm graphing.
So this is a more efficient way, the rectangular graph, a more efficient way to do just like a T-chart, like.
You can do a T-chart for sure.
Like,
Yeah.
Would it allow the same stuff?
Yeah, would it vary at all?
This graph? Well, I mean, like if I graph these more accurately, like your T-chart's just going to give you the y values of here for all of your r's at different points. Because that's what this is representing for me. I'm viewing this as this was the r, right, the radius, and the radius is changing. Sometimes it's small, but the furthest it ever gets is, right, -2 away from things. So the radius is shifting. Sometimes the radius is 0, and that's what's going on. So the radius is changing depending on the angle. So I'm just visually trying to think about this is all. So
Alright, this may be a stupid question,
What's
but
up?
how would you solve it for the T-chart?
For a T-chart, I would have done a T-chart essentially like this, where I would have done input theta, output r, and I would have just plugged in some values of radians or something to that effect of 0 and pi over 2 and or pi over 4.
So this would only work in radians, not degrees?
No.
No, it would work. This one would, because sine, if you're in degree mode, can accept that and output the same ratio regardless of radians or degrees. So as long as you're in that mode, that's fine. So yeah, because the sine function can handle either. So the next interesting thing, the next window of space that I'm looking at occurs between pi over 3 and 2 pi over 3. So think about this. I'm looking at from this window to this window. This is what I'm analyzing right now, right? And in this window, what are all my radial values going to be? They're all negative. But at most, they get as far as -2. So think about it this way. I'm looking in this direction, but I'm graphing backwards. All right, so the maximum value is actually going to occur this way, but -2 backwards. So that's going to land back here. So this is really interesting. So once it got here, it actually starts mapping backwards and makes another pedal out this way. All right, yeah, those pedals aren't really amazing there, but you get what's going on. And then it's going to be positive R values for this next chunk of from here to here, is it? Yeah. For those angles, so once it looped back here, it actually would loop like this, and I messed up, didn't I? Let's see. Oh, it's right here is where it should hit 2, I believe. Yeah, because it's halfway between those. So yeah, so it's interesting analyzing this when it's positive and when it's negative for R values. And then the rest of it, it's actually going to loop back through this, and follow the same exact path another time. is what it ends up doing. Is what goes on. So that's kind of a interesting behavior there. Let me show you a graph of this. Let's see, what was our equation? 2 sine theta. So let's graph the following. 2 sine theta, and if I graph it, 3 theta, there we go. Sorry, thank you for the save, because I was just like, that is not the right graph. There we go.
That's how we do it.
So just to verify,
Okay.
right, so you can see that this is actually, right, not that bad. I was pretty close.
Technology these days.
So yeah, so there you go. So that's the idea. You can make a table of values. I like kind of visually thinking about it. We're not being super accurate necessarily, but it's interesting that you can get all these crazy loop-de-loops and twirls and whatever and flowers. So thanks for watching, internet friends. Bye-bye.